Hello everybody, this is Dr. Christopher White and welcome to part 2 of Sedimentary Rocks part 2, just to get even more confusing. Okay, so we're on to carbonate environments now. So carbonate rocks are dominated by limestones, which are composed of calcite, so calcite is calcium carbonate, CaCO3, and dolostones, which are composed of the mineral dolomite, so dolomite is calcium magnesium carbonate. It should be noted that most dolostones are actually altered limestone. So primary dolomite isn't that common. Most of the time it's as part of the diagenesis process, so as part of taking your calcium carbonate rich sediment and turning it into a limestone. It's not uncommon for a hydrothermal fluid to move through your rock as it's being liquefied. And of course, if that hydrothermal fluid contains magnesium, the magnesium-bearing hydrothermal fluid reacts with the calcium carbonate and it produces dolomite. So we've discussed how carbonate sediments have a set of very specific conditions which, they will prefer to form in. So we're going to discuss those again in the next slide, so don't forget. It's also not uncommon for limestones to contain sand to gravel sized allochems. So an allochem is a carbonate particle. So it could be something like a shell fragment or something like an ooid. So these allochems can be thought of in a similar way to clasts. So for instance, you can get things like shell fragments being moved around by wave action, and you'll actually get the shell fragments forming symmetrical ripples within your carbonates. So the same kind of processes that can happen in marine sediments of a clastic nature can also happen in carbonate sediments as long as they have allochems in the sediment, so as long as there are particles which can be moved around. There's normally also a micrite component. Micrite is referred to as lime mud. It's very, very, very fine-grained calcium carbonate. So when you actually pick it up and touch it, it actually has that kind of muddy feel to it. However, if you take some of it and pour a bottle of Coke or Pepsi over the top of it, you'll very quickly see that the acid in your Coke will actually react with the calcium carbonate and you'll get a chemical reaction going on. You'll see it'll literally fizz. So you can distinguish between micrite and regular mud quite easily. Now, the one thing is the presence of micrite means that the environment in which the carbonate must have formed had to be protected. And that's because micrite is a lime mud, it's very, very easily transported away. It's very, very easily lost. So you can only get micrite building up in large concentrations in protected environments. However, unlike detrital sediments, the particles that make up limestones formed in or near the environment of deposition. They're not really transported in. So you can say with a relative degree of certainty that when you see a limestone, that was the location in which it formed. Everything you can see in the rock formed at that location. So as carbonates form in marine environments, there will be some degree of sediment reworking, especially if there are these allochems present. And this means that you can get crossbeds in your limestones, you can get ripple marks, and in some cases, if your micrite gets exposed and is allowed to bake in the sun, you can also get mud cracks. So you can get the kind of textures you would see in a regular clastic sediment also appearing in carbonates, and we can interpret them in the same way, because it's the same basic processes that form them. Now, although limestones can form in lake environments, the vast majority will be deposited in the oceans. And of course, the conditions that we want to, really improve our chances of getting a limestone forming are, we want warm water, shallow water, so that's between 0 and 200 meters water depth. We want clear water. We want our water to have a normal salinity. And we want our body of water to typically be 30 degrees north or south of the equator. That's typically where we have nice warm water. So carbonate shelves, which are the main environment for forming large quantities of limestones, are located on the continental shelf in water depths between 0 and 200 meters. There's another type of carbonate forming environment which is called a platform. And this forms on regions of high topography, usually seamount. So a seamount is a extinct or active seafloor volcano. And sometimes these volcanoes will grow so large that the peak of the volcano will be sitting just below the water's surface. So essentially, because it's so close to the surface, you have a water depth of between 0 and 200 meters. And in that instance, you can then get reefs developing on the top of these seamounts. So deposition occurs in environments where there is little detrital sediment, especially mud, because we need that clear water. If your seawater is full of very fine-grained muddy sediment, that is going to significantly reduce the chance of you forming carbonates. So if you think of the types of environment where you form large quantities of carbonates in the modern setting, so think of the Caribbean for instance, you instantly think of clear blue water. And that's exactly the kind of water you want if you want to form limestones in quite large concentrations. So carbonate shelves are the dominant location for carbonate deposition. That's purely because these carbonate shelves can have quite a large surface area, and as such they can form quite large quantities of carbonate. So the shelves will often feature a raised area referred to as a carbonate barrier. And the carbonate barrier will typically be located just before the shelf begins to drop away into deeper water. So your carbonate barrier will very often form at the edge of the continental shelf just before the shelf breaks, so just before you start coming down the continental slope. Carbonate barriers form in moderate to high energy environments, and they are typically reefs. Okay, the reason that reefs like to form in these environments is there's a constant water movement, so you have deep water coming up from the abyssal plain, so down the continental slope. You also have material coming off the continents and heading into that area, so you get lots of material meeting at that location, which means there's loads of life, which means there's loads of food essentially, so you can have nice big communities. Some carbonate barriers are not actually reef related. There are some carbonate barriers that are actually made of skeletal particles, so bits of shell, or you can occasionally get carbonate barriers made up of piles of ooids. So an ooid is a little kind of jawbreaker-like carbonate particle that is less than 2 millimeters in diameter. So carbonate barriers tend to be structureless because most of them are reefs, and a reef, well, is quite a straightforward thing. A reef is literally just a pile of bits of dead coral. So all the shells from the coral organisms, when they die, the organic portion rots away, but the shell gets left behind, and over time, as more and more coral grows, you get more and more bits of shell accumulating. And so most reefs are just literally a pile of bits of coral. And obviously that means there isn't really going to be any structure. So we have our carbonate barrier here, and you'll notice it's located towards the shelf break. So this is going to be our continental slope. And so what we're going to have behind it is a protected body of water. Okay, this is sometimes referred to as a carbonate lagoon. And it's within this carbonate lagoon where we're going to get most of the carbonate deposition taking place. So within the carbonate lagoon we can get things called carbonate banks, and they're linear bodies of carbonate that form in the lagoon environment. And we can see these carbonate banks, they can contain crossbeds and ripple marks, suggesting the water depth is quite shallow and that the water is being agitated, it's moving. Also in these lagoon environments you will also tend to get micrite forming. As we've discussed, micrite being so fine-grained is very easily lost. So it's only in these protected environments where you can start to form quite large concentrations of micrite. So in terms of the lagoon sediments themselves, they will be micrite dominated, so lots of lime mud, but they will of course be absolutely full of fossils as well. So your carbonate barriers are most likely to be a featureless mass of coral fossils with bits of mollusk and sponge fossil mixed in there as well. And behind it you're going to get a fine-grained carbonate sediment which is going to be full of fossils. Your carbonate sediment may show crossbeds, may show ripple marks, and as we touched on the previous slide, could even show mud cracks in some extreme cases. And so you can see we have these two different environments, but of course they are both linked to each other. They're both made of carbonate. In terms of the micrite itself, you're probably thinking, well, how does this very, very fine-grained carbonate actually form? Well, micrite can form in one of two main ways. The first way is you can have calcium carbonate dissolved in the seawater, and some of that calcium carbonate can just precipitate itself onto the bodies of little organisms living in the water, typically these little single-celled photosynthesizing organisms. And so you'll get these little crystals will nucleate on the bodies of the animals. It doesn't really hurt them, and they just live their lives. They die. Obviously the organic portion rots away, but the fine-grained carbonate crystals which are on their body, well, they float down to the bottom of the lagoon where they become incorporated into the micrite. The other way that we can form micrite is due to biogenic destruction of larger carbonate particles. So what I really mean by that is bits of shell in most cases. So if you've ever seen an oyster shell and looked at the outside of it, you'll know that an oyster shell consists of layer after layer after layer of calcium carbonate. And as the shell is growing, sometimes as a new layer gets added, organic material will get stuck between layers. And so this means there's food essentially trapped in the shell. And there are certain types of organisms that can burrow into shells in the hope of finding these bits of organic material stuck in the shell. Now, obviously, the animals are there for the organics. They're not there for the shell. So essentially, as they bite their way through the shell, as they eat through the shell, they can't do anything with the calcium carbonate. So they just, for want of a better way of describing it, poop it out the other end. And so obviously, the material they release is going to once again be very, very fine-grained calcium carbonate, which will become incorporated into the micrite. So those are the two main ways in which we can form these very fine-grained micritic deposits. So here's an example of a modern carbonate platform. So this is the Florida Keys. So you can see this is obviously the east coast of Florida, so down in the southeast. Over here, off to the left, would be the Florida Everglades. But you can see here we have Key Largo. So you can see here's our carbonate barrier. Okay, and this is actually an old carbonate barrier. This is an old reef, or at least that's what it's based on. So this once upon a time was underwater, but the sea level dropped and it became exposed. So this carbonate barrier is protecting a body of water behind it. So this is our carbonate lagoon. And you'll see, number one, the water here has a very creamy white colour to it. And that's not due to clastic sediments coming off the land. That's due to all the micrite, all this lime mud. It tends to give the water a kind of creamy white appearance. And so we can see that here. So that's a first indicator. There's lots of carbonate lurking here. We can also see within the lagoon we have these carbonate banks, these linear bodies of carbonate that build up. These are the environments that might show things like crossbeds and ripple marks, and maybe if the micrite is exposed above the level of the water, you could even see mud cracks. And you also have patch reefs. These are small reefs that form within the lagoon. So obviously you have the main linear reef here, and then in the lagoon itself you can get these small patch reefs. And these small patch reefs are linked together by the carbonate banks. And so this is the environment in which we're going to be forming very large quantities of micrite. And of course, because it's protected, the micrite is safe there. Now, what you can actually see, if we look further out, you can actually see there is a feature coming up along here. And this is actually a new carbonate barrier forming. So there's a new reef environment forming along the slope break here. Okay, so there's actually a new carbonate lagoon, a very linear one, between the old carbonate barrier and the new carbonate barrier. So we have a new carbonate lagoon forming right here. So this is kind of the classic example of a carbonate shelf. Now I will be honest and say this is a very small example. Okay, so this isn't actually going to form huge quantities of carbonate. If you want to form huge quantities of carbonate, you need to be looking at a system like this. So now we're looking in the northeast coast of Australia. So this is the Great Barrier Reef area. So what you'll see is here we have our continent. Here we have our shelf break is coming along here. So this area here is going to be our continental slope. This is our abyssal plain over here. So this is our shelf. You can see the reefs coming around here along the shelf break. So that's our carbonate barrier. And so these reefs are going to be protecting the body of water behind. And this is a very large body of water. Now, At the moment, as you can see, there are still quite large gaps between the reef bodies, and so that means water can come in and out quite easily. So you're not going to get a build-up of very, very large quantities of micrite yet. You need these, these barriers to be a little bit more continuous and robust before you can really start to build up micrite. But if these barriers are allowed to link up to form a pretty solid defense, then all of a sudden you will have your isolated lagoon back here, and you will begin to form quite large quantities of micrite, because you have warm water, you have clear water, it is shallow water, has a normal salinity, and you're approximately 30 degrees north or south of the equator. So all the other conditions are met for very large scale carbonate formation. Now, one of the things you might be thinking is, well, hold on a minute, Australia is quite a large continent, so you would expect quite large rivers, which should be dumping quite large quantities of clastic sediment along this coastline. Well, the situation is that because the northeast of Australia is quite a dry place, it means you don't have many large rivers, and so that means you don't have much clastic sediment being deposited along the coast, and as such that helps to keep the water quality very, very high, so it's nice clear water. So although this area of Australia isn't quite ready yet to be a full-blown carbonate lagoon like we can see here in the Florida Keys, give it a few million years and it will be set up perfectly. That is, of course, assuming the Great Barrier Reef survives. Okay. So in contrast to carbonate shelves, carbonate platform environments exist because there is a topographic high big enough to produce an area of shallow water. And of course the most common of these topographic highs on the seafloor will be a seamount. And these platforms will develop a carbonate reef on the windward side of the platform, and that will protect a carbonate lagoon directly behind. So here's quite a nice example. So this is off the north coast of Venezuela. Okay, so this is our carbonate platform here. So beneath this there is a seamount, an extinct volcano, and the peak of the extinct volcano is coming within 200 meters of the water surface. We also happen to be in an area where the water quality is quite good, the water is warm, it's shallow, it's relative, the salinity is normal, and we're 30 degrees north or south of the equator, so we meet the requirements for carbonate formation. So what can we see? Well, this is the windward side over here, so the wind is going to be coming from the east and moving off to the west. And so that means this side of the platform is the one that's getting hit by the water being pushed by the wind. And this is the location in which we're going to form our reef, because the water being pushed along by the wind essentially brings food with it. So this is where the coral reef is going to start forming. And you can see the reef itself continues all the way around, continues all the way from the northwest, all the way down to the southwest. So it, pretty much completely loops the platform. So behind the reef, obviously, we have our carbonate lagoon, and you can see this creamy white colour here. So you can see the build-up of carbonate material in this protected environment. In fact, you can actually see, for instance, here, these very light areas, that we have very large concentrations of carbonate building up. So, we have quite a lot of material. And so this cross-section here is kind of showing you the general situation. So on the windward side of our platform, we're actually going to have our reef itself, which is going to be right here. Okay, so if the reef gets above sea level, obviously it will form an island. At the moment, the reef along here is below sea level, got above sea level over here. Behind our barrier, we're going to have these tidal flats. So this is the area where carbonate is being moved around by tidal processes and wave processes. Behind it, we have our carbonate lagoon, which contains our carbonate mud. And sometimes if we have carbonate particles like ooids and bits of shell forming, we may start to build up things like a pellet sand or mud, which is a mixture of carbonate and allochems, and then we may build up a concentration of slightly coarser material, so like bits of ooids and bits of shell can build up along the backside of the platform. But once again, what we've ended up with is a carbonate barrier, which is protecting a carbonate lagoon directly behind it. And it's, of course, in this lagoon where we're going to form most of our carbonate, and that's mostly going to be this very fine-grained micrite. Okay, so what about evaporites? Well, obviously an evaporite is produced when we have our seawater evaporating away. So we need to come up with a situation where we can, isolate a body of water and make it evaporate. So evaporite sediments are dominated typically by a couple of minerals, or groups of minerals, should I say. We have the halides, so that's the salts, so that's minerals like halite and sylvite. And we have the sulfates, so that's minerals like gypsum or anhydrite. So these minerals are extremely common in marine evaporite deposits. Okay, and so when we start seeing large concentrations of either halite or gypsum, we begin to instantly start thinking, right, we're probably looking at some kind of evaporite deposit. Now you can get smaller evaporite deposits associated with player lakes and saline lakes, but these are environments that tend to form on the continents, and so they are obviously not technically considered marine. So most of the time, marine environments will tend to be slightly larger, and they'll tend to give us, bigger concentrations of evaporite minerals. So if we want to form a substantial deposit, we can only really do that if we form a restricted body of water, which is an ocean or a sea basin of some kind. So evaporites are far less common than detrital or carbonate sedimentary rocks for a couple of reasons. Number one, you need to make sure you meet the criteria to form them. And the other problem is that some evaporite minerals, like halite, are soluble in water. So you can, in theory, form a nice thick layer of halite, but then let's say your sea basin refills with fresh water, well, that's going to dissolve the salt that's been precipitated out, isn't it? So you're going to lose that layer. So you can destroy evaporite minerals, or and the conditions you have to meet have to be very, very specific. So that limits the chance of you forming them. So locally, evaporites can be very, very important. So for instance, large deposits can occur in areas of Western Canada. So that's where most of the sylvite, the potassium chloride, comes from, that's used in a lot of fertilizer in North America. You have large quantities in Ohio, New York State. These are typically, and of course Michigan as well. These are evaporites related to the formation of smaller inland seas. And we have very, very large evaporite deposits associated with an area called the Zechstein, which was a kind of a body of water about the size of the Mediterranean that formed in the Permian. And that body of water completely evaporated away and left a body of salt that stretches all the way from the east coast of the United Kingdom all the way over to the east coast of Poland. So that's a very, very large body of evaporites. So just to give you some idea of what kind of thickness of evaporites you can form if you actually get a large body of water to evaporate away, there is 2 kilometers of evaporites underneath the Mediterranean Sea seafloor right now. And they were formed the last time the Mediterranean Sea became isolated and evaporated away. So that shows you the sheer quantity of material which can be deposited if you get one of these large bodies of water to evaporate. So the exact conditions for evaporites are actually a little disputed. We have the general conditions down, but obviously between locations there's going to be variation. So no one can quite agree on what the exact criteria you want to meet are. But in general, the basic criteria we have to have are, number one, our body of water has to be in an arid region. So you would prefer your area to be naturally hot and naturally dry. You also want your body of water to be restricted. So that means that essentially it's trapped there. Okay, so the Mediterranean is a great example of a restricted body of water. The only communication the Mediterranean Sea has with the Atlantic is via the Straits of Gibraltar, which is between Spain and Morocco. So that's a very, very small inlet there, so not much communication there. And obviously you get some water being put in by major rivers like the Danube or the Nile. However, their input is also relatively small compared to the body of water as a whole. So what you have is a restricted basin, so a body of water that's essentially got relatively low rates of communication with other water sources. And finally, you want rates of evaporation in excess of the rate of replenishment. So you want to be losing more water to evaporation than you're having put back in. So as long as you can meet these 3 criteria, you've set yourself up to be able to produce evaporites. So the conditions for forming large quantities of marine evaporites are often best achieved in coastal regions. and obviously in arid areas. So somewhere like the Persian Gulf is a prime example of the type of environment in which you could in theory form very, very large quantities of evaporite minerals given the correct setup. So here's one of the examples we typically deal with. So what we want is an isolated body of water. So in this case, I've just gone for a very simple situation. So here we have a lagoon. Now I know technically a lagoon is a transitional environment, but I'm just trying to use this as a way of getting the point across, a way of describing the process in general. So if the water input from rivers or the oceans is sufficiently restricted, it obviously means we'll be losing more water to evaporation than is being put back in. And so this means over time we will lose water. Now obviously, we've already touched on this in the past, as the water evaporates away, it can't take the dissolved minerals with it, so it has to leave them behind. And so as the water evaporates away, all the carbonates, the sulfates, the halide minerals that are dissolved in the water have to be left behind. And so this means the body of water that remains becomes more and more saline, so it becomes saltier and saltier. And also means the water becomes denser and denser, it becomes very heavy. And so what's going to happen is over time, as more and more water evaporates, eventually you're going to reach the point where you start crystallizing minerals. And typically, once you've lost about 50% of the water, you might see carbonate minerals appearing. So that's calcite. Now the problem is that calcite isn't really a particularly great mineral for telling you you're in an evaporite environment. So because we know that calcite can also form on carbonate shelves. So the presence of calcite doesn't really give us too much information. However, once we've gotten rid of about 70 to 80% of the water, we will start to see the formation of gypsum. That's calcium sulfate. And now that is a mineral, an evaporite mineral. So once we start seeing that, we can begin to say to ourselves, right, what we have here is a restricted body of water evaporating away. And then finally, once we've gotten rid of some 80 to 90% of the water, that's when the salt will start coming out in a big way. And so often what you'll see is a sequence of evaporites that will go from carbonates at the bottom, followed by sulfates, normally gypsum, followed by halide minerals, most commonly halite. And then after that, you'll get a range of lower importance minerals forming. So minerals like sylvite, potassium chloride will typically come along later towards the end of the evaporation process. Okay. So, do you know what? This is probably a good place to stop, actually. So, stop the presentation, get up, have a walk around, take a few minutes, relax, and then come back for part 3, please.